got a picture that looks like this. X-axis, Y-axis. Here's my x of naught. Here's my x of 1. Here's my x of 2. I don't know what my curve looks like. I just don't care. And I'm going to choose those 3 points upstairs, here, here, and here. F of x of naught, f of x of 1, f of x of 2, and I will find the one parabola passing those 3 points. Here it is, by the way, is this. Because I might get lost in my subscripts, can I be really lazy? Instead of referring to these chicks being located in the x-axis at x of naught, x of 1, x of 2, let me do something fancy. How about negative h, 0, h. Then I think the area under the curve over the first 2 subintervals can be approximated by the area underneath that first parabola, which is the integral from negative h to h of this beast right here. You guys, these are just monomials. These are an absolute piece of cake to anti-differentiate. Doesn't that give me this?
Why don't you exploit symmetry?
Can you say that one more time? I'm sorry. I missed that.
Oh, why don't you exploit symmetry?
You know, I would if I knew, for example, that this x term did not exist if b were 0. But my picture's too nice, David. Watch. That point could be here, this one up there. The parabola doesn't necessarily have symmetry with respect to the y-axis. I didn't mean to suggest with my picture that the parabola did have that symmetry. I didn't mean to.
Okay.
And I think in evaluating, that gives me this. Oh, yeah, you guys, again, are making me do all the work. Is that a 2/3 AH cubed? Plus 2CH. And if I were to massage just a tad bit and pull out both a factor of h and a factor of 3, I think what's left over is a 2a squared plus, is that a 6h?
What?
Is that okay?
What happened to the h in the first?
Yeah. It completely disappeared. I have no idea why, but it completely disappeared. Sorry. Is that better?
Well, if you pulled out an h, wouldn't...
Aren't I?
And you don't have an H.
And I think I have a C as well. Okay, so I don't know my math D. Is that better?
Sort of, you still have an A squared.
Wow, I'm just a complete mess.
Maybe you thought that was your h.
And you guys, let me rewrite this. Can I rewrite this way? As an h over 3 times, I got an idea. How about AH squared? Oh, but I got 2 of them.
Where'd the 2 go?
There it is.
Oh, okay.
And look at the CH. I can think of that as a plus C. Plus C. I know I'm being goofy, you guys. Just watch me for another brief moment. 1C plus 2C is 2C's. Oh, it's 6 of them. I missed something. I'll put it in. Now, I want you guys to take a peek at what's above this squiggly line. Technically speaking, you think when it comes to h, or AH squared plus C, look at my original function. I think if you were to evaluate this function right here, at negative h, you get this. I think if you were to evaluate this function at positive h, you get this. And if I think you added those 2 together, the 6h and negative 6h will cancel. And so I think what's above the squiggly line really comes from my y function evaluated at negative h. And I think what's above this doubly underlined expression is simply the result of when you add those together, what came from y evaluated at positive h. And I think lastly, shoot, what did I miss? Darn it, I missed the circle term right here. Well, technically speaking, if you were to evaluate this function at 0, wouldn't you just get c?
Yes.
Well, that being the case, I can interpret the 4c as 4 times y is 0. Or shall I say, this is simply my delta x over 3 times my function f you've added the first input, plus 4 times my function f you've added the second input, plus 1 times my function you've added the third input. And I think when it comes to the Simpsons rule,
Is it normally a short interval that we're evaluating the Simpsons rule? Because if you're doing...
no, not necessarily at all.
Because it's going to be tediously long if it's not.
Yeah, I know. That's why a lot of times you use technology.
Okay.
You just covered it up, but you have AH squared plus C at the beginning and at the end. Are those the same? Because on here you have Y, negative H, and Y.
You know, you're right. I was just trying to save room. There is something slightly off. It's this. With my blue pen. That collectively is y valued at negative h. This collectively is y valued at positive h. I just didn't put in the blue terms because they cancel each other out. So I really meant them to be there. And everybody check this out. Watch. Let's look at the explicit formula for generating Simpson's rule with n subdivisions. I think here's my f of x of naught plus 4x f of x of 1 plus 1 f of x2. But now when I look at the area underneath the next parabola, which shares its left endpoint with the right endpoint of the first parabola, I double up on that endpoint. That's exactly why this pattern recurs over and over again, except that the two extreme values of f, evaluated x of naught, and x of n, they're only counted once. That's where the pattern comes from. So again, go back to the pattern. Coefficients on the outside are 1. Ints are next from the outside are 4s. Then 2s and 4s and 2s.
So, do we not, like, we skip 2 because then we can have a change in concavity? Like,
It's
why
not
don't we
that-
go over 1 and then use the next 2 times?
Because I'd be missing a whole gap in here. That's why when it came to the first parabola with the 3 red points here, I looked at the area underneath that parabola, done.
Yeah.
But to look at the area underneath this next successive parabola with the green points, I've got to share that endpoint.
Oh, I know, but I'm asking why don't we share 2 of those?
I'd be counting the area twice. Think about it. One.
Oh, yeah, alright.
Did you see it? And I don't want to double up counting the area. That'd be weird, even if it's just an approximation. Notice something else. For that first parabola, how many subintervals do I need?
2.
That means for any collection of parabolas, I need even number of subintervals. There are 4 from now on. If you're going to use Simpson's rule, you need even number of subintervals. Otherwise, it does not apply. So you guys, I have more than 10 minutes left. Can I finish up with 2 examples, one of which I'm applying Simpson's rule directly, second of which I will ask a more sophisticated question, which is, how many subintervals would I need to get a desired accuracy using Simpson's rule? So, first things first. You guys, did I consider the examples today? No number 1. Oh, I did. Remember with the trapezoid rule?
Oh, yeah.
You didn't explicitly write it down.
Ah, I see your point. Everybody, somewhat of a silly question in the sense that you and I can evaluate this integral exactly. But just for practice, for the purpose of practice, let's get a practice using Simpson's rule with 6 subdivisions. I think Simpson's rule says this. An approximation for this value is going to be my delta x over 3 times f you've added the first endpoint plus f, etc., etc., etc. And I'll be careful with my coefficients. And everybody not being careful with the entire graph, let's be this lazy. If I'm really integrating from 1 to 3, let's just talk about where these ticks are if I subdivide this interval, bless you, into 6 subintervals. Well, here's cutting in half. I guess I'll cut the remaining 2 portions in thirds. If you guys trust my arithmetic. So I got my ticks. And so I think in the end, my delta x is going to be equal to third. My x of naught is going to be equal to 1. My x of 1 is going to be equal to 4 thirds. You guys okay with my writing so far? And let's just evaluate my function at these various different inputs. I think that's going to give me 1/9. So help me with this. Is it 1 plus? You're not going to help me?
3 over 4.
Times 4 is?
3.
I can't do it. Is that 3 over 2?
Yeah.
Do you guys mind? By the way, that's happiness, not factorial. Seriously, you mind if I don't do the arithmetic? I get a number. It's merely an approximation for the area underneath the curve. How accurate is it? I've got nifty little formulas I can use to approximate its closeness to the actual value.
That's it. That's all there is to it.
That's all there is to it using Simpson's law.
Really?
Really. What's that? I know. So that's what I'm saying. Maybe it was a lousy example. But at least, you know, in the end, if I really did do the arithmetic, you can see how far I'm going. By the way, part 2. I should have broken this up into 2 parts. Part 2. How accurate is this? In approximating this value. Okay, you guys, I know the board or the computer just went off. Check this out. Here's a tool in my back pocket identifying how accurate it is to use S sub 6 to approximate the value of the interval. The upper bound for the absolute value of the area is given by this expression. A and B are simply the endpoints, or the bounds of integration. N is how many subdivisions I commit to. Now listen to my choice of words in English. K is a number that is the upper bound for the absolute value of the 4th derivative function. So for me to answer part 2 of this first question, before I dive into my next question, let's you and I find the K value. Now to find K, here's my original function. Here's the derivative. Here's the second derivative. Oh, I don't know what it is. Is that a negative or positive 2 over x cubed?
I see where it gets something.
Third derivative is nothing more than negative 6 over x to the 14th. This isn't bad. His fourth derivative is nothing more than positive 24 over x to the 5th. Okay, let's stop for a second. I maintain that k is simply constant, which is the upper bound for the absolute value of the 4th derivative over the interval from, help me, is it 1 to 3? But over the interval from 1 to 3, is this function monotonic?
Mono what?
Monotonic. Is it strictly increasing or decreasing?
Decreasing.
Yeah, I think it's strictly, well, it is monotonic, actually strictly decreasing, isn't it, in the right-hand plane? So I think that being the case, is strictly decreasing, and it's always positive over that interval, so clearly, k is going to be nothing more than the valuation of my 4th derivative function divided by the left endpoint. which I think in this particular example simply ends up being 24.
The left-hand corner.
Well, yes, I think this function right here has some function over the integral from 1 to 3. Is strictly decreasing. And so I think its largest value in absolute values is going to be at the left endpoint, since all the y values are positive for the fourth derivative function. And, shoot, I haven't answered my question, darn it. I think an upper bound for the absolute value error in using Simpson's rule with 6 subdivisions for that integral up there in purple is going to be nothing more than my k times b minus a. Well, b minus a is just 2, isn't it? Raised to the power of
3.
well, for Simpson's rule.
Oh, Simpsons. Okay.
All over 180 times my n value raised to the 4th power, but n in this case was 6. And so I get g mine. That number represents how far off it is to use Simpson's rule with 6 subdivisions for this particular interval.
What's the upside down A subdivision?
My apologies if I've never used it in class. If ever I use an upside down uppercase A, it simply stands for the phrase for all or for every. I didn't make it up. We got a name for it. It's called the universal quantifier in symbolic logic. Well, can I ask my last, most significant? So you guys allow me, this will be my last question for the day.
Do we have to, is it one of those things where if you've seen it, you have to know it?
No, thank you so much. Here's what I expect of you guys by the next exam. I expect you to know what these formulas are for these various different rules. Don't commit these to memory. They're really important. It's just on an exam situation or a quiz situation, if you need them, I'll give them to you one form or the other. I may slap them on the board or on top of the exam. I just won't tell you which one to use when. But if you need to use it, then you'll have them available. You guys, what about this question? How many subdivisions do I need in order to use S of n to approximate this integral right here? Accurate. Shoot, how about 1/10,000? I think that's a realistic question in the sense that before I dive in and use Simpson's rule, I'm going to identify how many subdivisions I do need in order to get a desired accuracy. Yes, sir.
Do we have to use Simpson's rule? Can we use the error for the trapezoid?
Well, if I ask a question directly, which is how many subdivisions do I need for Simpson's rule to approximate to that kind of accuracy, then yeah, specifically that formula.
I didn't see the answer.
Well, let's give it a shot. Let's first find out what k is going to be. And to find our k, I need my fourth derivative function. You guys help me with this. F of x is directly x minus, I made it up, I don't remember this.
6.
Thank you. What's this first derivative?
It's the x.
Plus x minus 6. But that's just x minus 5. Oh, shoot, we're running out of class time. Don't we see a pattern? Do you guys agree? So question, does that function appear to be monotonic? Well, I think the answer is no clue. It's not very obvious. And if I can't tell if that function is strictly increasing or strictly decreasing, and I want to try to maximize its absolute value, what am I going to do?
Plug in the two extremes.
But what about something in between that might go crazy? like a critical number, which means I'll use math 30 to differentiate my fourth derivative function, which means generate the fifth derivative function. Ah, shoot, look at that. I think the only critical number I generate is 1. So let's you and I take our function f, evaluate at the left endpoint, evaluate at the right endpoint. Oh, shoot, it was one of my critical numbers. So I guess in the end it does become monotonic. And let's see, which one's the biggest? Well, f evaluate at 1 is, I really don't have any idea. I'll go right here. I guess it's just negative 5 times e to the first. But I think f of 4 is 3 times e to the fourth. In absolute values, I get these two numbers. Would you guys mind if I don't pull out my calculator? Clearly, that is the largest output.
Why
That'd be
is
the
it
case. What was that?
30? Why is it 30?
Well, I was simply plugging 4 in. I have no idea. I plugged it in down there. I'm so sorry. You guys, let's come back. If I plug 4 in for x, what do I get?
-2.
You know what? It doesn't matter. I still think by far in absolute values is so much larger than the previous one. So I maintain to find the value of n, how many subdivisions I need to get that kind of accuracy, I'll simply pull out my formula, chicken tooth theory, which is nothing more than my b minus a to the what power? Times my k, all over, you might not remember the coefficient, but it was 180.
180, n to the 4th.
Times n to the 1 less power. We're going to force this thing to be less than or equal to 1 over 10,000. It's just that I already found my k value to have an upper bound of 2 times e to the 4th. My b minus a is going to be 3 minus 1. But it's raised to the 5th power. Oh, is it 4 or 3? Thank you guys, I lost it. You said 4 minus 1? All over my 180 times n to the 4th power, I'm going to force this to be less than 1 over 10,000.
And it's 10,000 because of the 1201.
You know, I made the number better than there. I was just thinking this number. And if I were to solve for n, I see that n to the 4th power is at least as big as this nasty business. Well, that being the case, I think n itself then is going to have to be at least as big as the 4th root of all that garbage. You guys, only to save time on the clock because we're out of time, do you mind if I just give up and not pull out my calculator? I can just leave it to you. It's just some number, isn't it? By the way, what if we're this? What would you choose n to be?
6.30?
Perfectly put. It's got to be an integer, and it has to be even. And if you want this desired accuracy, n has to be at least as big as 6.2, but the smallest positive even integer bigger than 6.2 has to be 8. So if this were the answer here, I just made it up out of thin air. We will choose n to be equal to 8. Awesome. You guys, since I'm so late, can I bother not putting up a assignment until tomorrow?
Yes.
You're not going to look at it anymore.
No.
I didn't